Welcome back. So today we're going to take a look at chapter 6. This is called The Restless Earth. And if you recall from our last lesson, we did introduce to you the theory of plate tectonics. And so from that, you would realize that the Earth is a very dynamic place, and so restless, most indeed. And so this chapter involves our study of earthquakes. So we'll be looking at some of the locations that we see our earthquakes, how we rate them on our scales, taking a deeper look at the seismic waves, the seismic activity. We will also be looking at some geologic structures, so the deformation of the earth and what some of the terminology is for that. And we end it with a little look at the mountain building, which we did introduce to you with some of the plate tectonics on how some of these mountains, some are volcanic mountains, but others are just these continental convergent type of boundaries that build up our mountains. So we'll end kind of with a brief look at the mountain building as well. So most of Earth's seismic activity, the volcanism, like I mentioned, and the mountain building can be very well explained by the plate tectonics that we introduced to you in the last chapter. So if you need to go back and review that, please do so. I've got a little USGS, so the United States Geological Survey, that lists sort of the locations across the United States that has seismic activity. Of course, we think of seismic activity here in the United States. We always tend to think of California, the West Coast, definitely. So here we have color-coded. Highest hazards are the reds and the oranges and such, and then lowest hazards as we go down, the blues and such. And so yes, California definitely does have that higher, tends to be on the higher end of the risk. And again, plate tectonics, that is a boundary. That is an oceanic continental convergent plate boundary, if you recall that. So there is that subduction zone, lots of activity occurring along there, as well as we mentioned that transform fault of the San Andreas fault too, giving us a lot of activity. But what might surprise you is across here within, so a mid-continental seismic active region, this is not at a plate boundary. And so we need to think, well, what's going on there geologically to cause the seismic activity? But right around here, including parts of Arkansas, we've got Missouri in there as well. There is an ancient, very ancient, we're talking 750 million years ago when this occurred, but there was a pulling apart, so a rifting, a divergence occurring within the continental mass. And it didn't split the continent all the way apart, but it did cause this rift. And so every now and then it will activate. And so we will be talking about the New Madrid fault zone that's in and along here. And occasionally we do get some activity that is felt here in Arkansas from that. Then there's these little other small places out there in Oklahoma, one little one out there in Kansas, and those tend to be attributed to the hydraulic fracturing or that fracking drilling method that we talked before about in the introductory chapter, where because of the drilling method and they're setting off those little explosions, and then they're putting that fluid down into the earth, the waste of it, and that destabilizes the foundation, and so you can get slippage and some motion occurring from that. And so those little places are explained by more of a man-made scenario rather than a geologic feature within there. But yeah, some of these locations might surprise you that we do have some seismic activity in there. And so this was, every now and then they update these, and so this was from 2018, their latest update with that. And so that New Madrid earthquake that I mentioned there there was a major one back in 1811 through even to 1812. And it was the largest on record for a mid-continent type of an earthquake. So not at a plate boundary, but within a mid-continent. It was one of the largest on record. And I do have this was actually before they had the Richter scales to where they could place it on the Richter scale, but it was between a 7.3 and a 7.5 on the Richter scale. But what they used to kind of gauge that was people's writing. So a diary or a newspaper where people were describing what they saw and what they felt. And so I have a little excerpt from a George Heinrich Christ, who lived back in the 1800s when this New Madrid earthquake occurred in 1811, and it also continued through to 1812. And so I would like to read to you some of the excerpt from his diary. So the way I'm speaking here is more the way he wrote this when I read it to you. But this is December 16th, 1811, and he says, "There was a great shaking of the earth this morning. Tables and chairs turned over and knocked around. All of us knocked out of bed. The roar I thought would leave us deaf if we lived. It was not a storm. When you could hear, all you could hear were the screams from people and animals. It was the worst thing that I had ever witnessed. It was still dark and you could not see nothing. I thought the shaking and the loud roaring sound would never stop. You could not hold on to nothing, neither man or woman was strong enough. The shaking would knock you loose like knocking hickory nuts out of a tree. I don't know how we lived through it. None of us was killed. We was all banged up, and some of us knocked out for a while, and blood was everywhere. When it got daybreak, you could see the damage done all around. We still had our home. It was some damage. Some people that their homes were not built strong did not. So their homes didn't make it. But his did. We will have to hunt our animals. Everybody is scared to death. We still don't know if anybody was killed. I made my mind to one thing. If this earthquake or whatever it was did not happen in the territory of Indiana, then me and my family is moving to Pigeon Roost as soon as I can get things together. So he was going to get out of there and he was going to go towards Indiana. At that time it was still a territory. Indiana, and he's going to Pigeon Roost. And so he was talking about the passenger pigeons that are extinct nowadays, but at one time they were just everywhere. People would kill them and eat them. So there was a town in Indiana called Pigeon Roost that he was headed for. He thought things would be better there. So that was December 16th. Now we're into January 23rd, 1812. So it spanned from 1811 to 1812. What are you going to do? You cannot fight it because you do not know how. It's not something that you can see. In a storm, you can see the sky and it shows dark clouds, and you know that you might get some strong winds. But you cannot see anything but a house that just lays in a pile on the ground. Not scattered around, and trees just fall over with the roots still on it. The earthquake, or whatever it was, I mean, they're still not sure, has come again today. It was as bad or worse than the one in December. We lost our Amanda Jane in this one. A log fell on her. So things falling on people or has an extreme hazard during an earthquake. So their dear little Amanda Jane died in this one. So this is more or less an aftershock of the main quake. We will bury her upon the hill under a clump of trees where Bessie's ma and pa is buried. A lot of people think that the devil has come. Some thinks this is the beginning of the end of the world. February 8th, 1812, so another month goes by. If we do not get away from here, the ground is going to eat us alive. We had another one of them earthquakes yesterday, and today the ground still shakes at times. We are all about to go crazy from pain and fright. We cannot do anything until we find our animals or get some more. We have not found enough to pull the wagons. So that was their means of transportation. They needed their animals. March 20th, so yet another month goes by. I do not know if our minds have gone bad or what, but everybody says it. I swear you can still feel the ground move and shake some. We still have not found enough animals to pull the wagons, and you can't find any to buy or trade. April 14th, so about another month, 1812. We lived to make it to Pigeon Roost. We did not lose any lives, but we had plenty troubles. As much as I love my place in Kentucky, I never want to go back. From December to April, no man, woman, or animal, if they could talk, would dare believe what we lived through. From what people say, it was not that bad here, so in Indiana. They felt the ground move, so even there, they felt the ground move and shake, but it did not destroy cabins and trees like it did in Kentucky. So even that far away in Indiana, they were still feeling it. So this is called the New Madrid earthquake because of that fault line that I was telling you about, the New Madrid. I'm going to abbreviate earthquake with an EQ there, but this was of 1811 to 1812, okay, is the largest quake on record for a mid-continent, okay. So they didn't have the seismic stations when this was all going on, so accounts like George Christ here, his diary, is what they used. So trees falling over, many of their homes destroyed. Now, George lived in a log cabin, and he said his did better than some of the other homes that weren't built as strong as his. And so wood, the material you build with, becomes very important, and the wood tends to flex a little bit, so it's a better building material. His area that they ended up getting to, got a little picture of that we could go to maybe here. So this is the fault zone all along and through here, the New Madrid fault zone in there. That ancient rift that was, kind of like an ancient scar of a rift zone, a tensional type splitting of the continent there within. And so he lived in Tennessee to begin with, and he certainly felt it there. Oh, I'm sorry, he lived in Kentucky, he said, and he felt it there. That's where his cabin was. And of course, he was on his way over to Indiana. He was going to get out of there. And even they felt it. So here's the zone, here's the fault zone, and way over in Indiana, they felt it. So this was a very large, the largest on record for a mid-continent earthquake. Again, about a 7.3 to a 7.5 on the Richter scale is their best estimates from accounts like the diary of George Christ, newspapers that certainly reported on it as well. So a little bit that we do have something that could potentially activate. Every now and then it does activate. And so that does go through a little bit within Arkansas there as well. So little excerpt there from a diary account of the New Madrid earthquake of 1811, 1812. Okay, so what is an earthquake? An earthquake is when there are vibrations that are formed and go through and within and around the earth because of a release of energy. So anytime we get the motion of those plates, anywhere we're getting a slippage, it will release all that energy, and actually in all directions the energy will go from what they call a focus, okay, which is where the actual energy release starts, okay, and then it fans out in all directions from that original source in there. We call that the focus there within the earth, and directly above the focus but on the surface of the earth is called the epicenter, if it's right up above on the surface in there. And so if you recall, we introduced to you the term lithosphere, so the Earth's outer sphere, the outermost crust, so oceanic and continental crust, and then that uppermost part of the mantle, all of that together, sort of that cool, rigid, solid kind of earth material, that was known as the lithosphere. And so of course that's very brittle acting. And of course beneath that was the asthenosphere, that sort of hot plastic, and it does move, the basis of our plate tectonics. But yeah, anytime you do get a slippage or the motion, grinding or the breaking, so a fault line and motion along that, you can get that energy being released in the form of an earthquake, we call that. And so that energy is going out in all directions in what we call these seismic waves. And there's a variety of waves that we'll introduce to you, but they get recorded on sensitive instruments around the world. We would record these events, but at the time of that, 1811, 1812, we didn't have that technology. But little sensitive instruments that will detect the vibration and actually give you some little squiggly lines. I have one here. This was from the 1964 Alaska, when they had their major earthquake. Here's a little piece of that. These little seismic waves get recorded. So it's a sheet of paper, right, on a drum kind of thing. And up here where things get kind of crazy in there. And so that instrument is suspended, and anytime there's a vibration, it will cause a deflection on the pin that's of this rotating drum, so the seismograph, and it will record any little deflection with an amplitude that goes up to record the shaking of the waves. And so this one got a little crazy there with, this was 1964, the Alaska earthquake. That was a major earthquake. Something interesting that I want to share with you is at the time when they had nice records, vinyl albums, they did a lot of interesting artwork on their record albums. And this is from the Doobie Brothers. Don't know if any of you are familiar with the Doobie Brothers. But Living on the Fault Line was one of the names of their song, was the name of the album, Living on the Fault Line. So out there in California, San Andreas Fault Line, there's sort of this misconception that California is going to just slide off into the ocean kind of thing. And so here they have the very top of the Transamerica Insurance Building. It's sort of this pyramid looking building. And here we have it kind of sliding off into the ocean there. And on the background here, y'all just see the steeple kind of that building out there in the ocean. But the interesting thing, you might not be able to see it from there. I'll try to put it under the camera. Their background that they have on their album is one of these seismograms, the recordings of an earthquake, so the waves. In there. So here, we'll put that one under here. Very artistic, I thought. The Doobie Brothers. Yeah. And so a little bit of that up towards the top there, we're seeing in their background, yeah, they've got the seismic waves that they're showing, the little amplitudes on there. And so that album was living on the fault line. But that's a misconception that California is just going to slide on off to the ocean there. But some very interesting artwork of a geologic seismic activity relating to some artwork. So geology really is everywhere. It surrounds us. That's just one more example of how geology is kind of rooted in our nature. Okay. So there's some terms for you, the seismic waves and those little amplitudes that get recorded. So there's the focus, and the focus is beneath the Earth's surface, within the Earth's crust, down in there. And then waves are going to go out in all directions from the focus. We call directly above on the surface, directly above the focus, we call that the epicenter. So maybe you've heard that terminology of the epicenter, but that's up on the surface of the Earth, directly above the focus, which is within. Okay, so we talk about earthquakes and we talk about faults. So the movement that produces earthquakes are usually associated with these large fractures. So the Earth, right, can move along those fault lines. So that line there, okay, is a fault. And you can get slippage. It can go down, it could go in reverse, okay, it could go side to side. So depending on our stress, you know, is it compressing? Is it that tensile one that you get the drop down, or is it sort of that shearing motion? Okay, so all manner of directions that we can get motion within and involving a fault line. Okay, and so most of that motion, the cracks are the fault lines in there. So Living on the Fault Line is that name of that album in there. But most of that motion along the faults can be explained by the tectonics theory, the plate tectonics we talked about last time, because those boundaries there, convergent, divergent, or transform, all along a fault line in there. So motion definitely is at these boundaries. But we did see that intercontinental, so a mid-continent activity as well in there. So elastic rebound, and so I kind of liken this to, you know, a little elastic rubber band here, that it's elastic like, so you can stretch it, but then it springs back to its normal shape. Okay, so if I was to stretch it too far, it might actually rupture or break, right? But then everything will spring back to its original size and shape, right? I'm stretching it out, but then it goes back to its shape. Or, you know, if I had a pencil, I don't have one. And you know how a pencil kind of flexes a little bit, but if you go too far, too much stress, it will actually then rupture and break and fracture in that. So these sort of rocks on both sides of an existing fault, they get deformed by those tectonic forces, the compression or the tension or the shearing, those forces, tectonic forces. So the rocks will kind of bend, and that's sort of storing up that potential energy, elastic energy, storing up some energy. If I was to release that, it would snap my finger, all right? So we get some frictional resistance holding the rocks together, that's overcome, okay? And then it gets released and it snaps back. And so Reed was the one that first kind of explained that elastic kind of rebound. So you get your slippage at the weakest point, which is the focus, and then vibrations. So the earthquakes are occurring as that deformed rock will, you know, spring back to its normal shape and size, original shape. Elastic kind of rebound that we talk about. And of course the energy is being released all the while. And so foreshocks aftershocks. Sometimes it's hard to distinguish between what's the main earthquake and then these leading up to and then even after. The little diary account that I gave to you, remember that George mentioned that the second one was even stronger than the first one. So an aftershock, yeah, it could actually even be larger in some cases. So sometimes hard to distinguish, but often are a little bit smaller earthquakes, the after shocks. And then foreshocks precede a major earthquake by days, sometimes several years. So it's really hard to predict an earthquake. Just because you're getting a little activity doesn't mean it's going to be a big one. So they still have a tremendously difficult time trying to predict and give any sort of a warning. But yet they're very intently studying these because any type of a heads up or warning system would be excellent to save people's lives. So you could evacuate if you knew in advance, but we just don't have that prediction ability just yet. Okay. Maybe we never will, really. So to study then our earthquakes, as I mentioned, these kind of seismic waves, that study is called seismology because you are studying seismic waves. And it dates back a couple thousand years to the Chinese, where they actually set up some rudimentary type instruments that could help them figure out the direction that the earthquakes were coming from. But the instruments that I was referring to, where we were able to get a seismogram from, so the little drum of paper that rolls past a deflecting pin when they get the shaking, okay, a seismogram, is coming from an instrument we call the seismograph. And so they're the ones that are recording any of the shaking that occurs. Okay, so the rotating drum and the little deflecting pin because of all the motion in there. So the seismograph does detect the ground motion, the shaking. Oh, and this one was the Chinese one. So they had little jade balls placed around, okay? And then depending on what direction the shaking was coming from, the jade ball would fall down into the mouth of the little frog down there at the bottom of the picture. I don't know how well you can see that one, but that could kind of help them figure out, okay, this was our direction of shaking, and how many balls fell off, also intensity. But here's a better look at what a seismograph looks like. So the rotating drum of paper, the pin that gets deflected because of the shaking, and then it rolls across and you can get the little amplitudes of the seismic activity recorded on that drum on a sheet of paper kind of thing. And they also have lasers that do that recording as well now. So, but more than one type of seismograph is needed to record both the vertical and the horizontal. So if you got shaking this way, horizontal, and you got shaking this way, the vertical motion as well. So all manners of motion there. But these are the seismograms. So that piece of paper with the amplitudes on it, the seismogram. Our seismic waves, so we have a few here that we talk about. The surface waves, these travel along the surface of the earth, the outer part of the earth. One that they talk about are called L waves. Let me see real quick. No, they don't really, I'm going to write that on the board. The L waves, okay, are surface waves. Okay. The love waves for the person that invented them. Love waves, his name was Love. And they are actually the ones that produce the most damage, these surface waves. So the L waves, the most damage from that. They cause the most damage. But very complex motion causes the greatest destruction. And so the slowest velocity, these arrive at the seismographic station the very slowest. But again, these are surface waves traveling the outer part of the Earth's crust. This next one here of the body waves, so these are traveling within the Earth's crust. There's two types of this that they talk about, primary or P waves. So our P waves, again, that's a body wave, standing for primary. And the reason they call them primary is because they are the fastest traveling waves. Okay, so it'll say it somewhere here. But these can travel through solids, liquids, and gases. So these are the fastest. So SLG, solid, liquids, and gases, so all manner of material. And another word, like if you need another P word for that, push-pull, push-pull. So I don't know how well this is going to work here, but I'm going to try to do it anyway. Say this slinky here, I really need something, table or something to put this on. But if I was to push and then pull, push-pull, push-pull. So this type, the wave ends up getting propagated, okay, through the wave. You can kind of see it go through. Push-pull, push-pull. That would be something like a P wave, okay, a compressional push-pull, push-pull type. So slinky, if you ever play with a slinky, that's good for that, and to envision that type of wave. The S wave, or the secondary wave, so an S wave. Okay, these are the slowest. Waves. They take a little longer to get there. But if you need another S word for this, shaking. So shaking like, shake motion, right angles to the direction that they travel. These only, and there's another S word for you, travel through solids. So travel through solids. Solids. Okay, P waves go solid, liquid, gases. These only go through the solids, and these are side to side or shaking type. Okay, I don't know. A nice table would be good, but sort of a side to side motion. Okay, so the other one was a push-pull P wave, side to side or shaking motion for our S waves. So these are body waves. Okay. The P and the S waves. But they do have differences, so we'll put body over here. Body waves. Okay, that's a surface wave. The L waves. These cause the most damage, but these are traveling within the Earth through solid, liquid, gas, compressional or push-pull. Slowest, secondary. S also stands for secondary because they are the slower, and they travel through the solids, and these are the shaking or the side-to-side motion. Okay, there. They're slower than your P waves, and that ends up becoming important because we can use the difference between the P arrival time and the S wave arrival times, and we can help to trilocate our epicenter of our earthquake using this seismic information. Okay, so we mentioned the focus. We have that little picture of the focus. That's the place within the Earth where the earthquake waves are originating. That's where that motion, some sort of slippage has happened, either through compression or tension or shearing motion. Got the motion going, and then we release the energy. And then the epicenter is directly above on Earth's surface, so terminology. Now, our epicenter, like I mentioned, is located, you can find it and locate the epicenter of the earthquake by these differences of the P and the S waves. They do have that little bit travel differences in their arrival time. So the S waves are a little bit slower. P waves get to the instrument first, and then they're followed by the S waves a little later. So yes, so that focus, you know, energy's radiating out in all directions, making its way to these little seismographic stations, which there are many, many located around the world, and then the instrument will record those waves when they reach those stations. Okay. Now, in order to get the epicenter of our earthquake, then we do look at that difference between the arrival time of the P waves and the arrival time of the S waves. So we need a minimum here of 3 seismographic stations in order to trilocate our pinpoint, the epicenter of our earthquake. And so at each of those different stations, those 3 stations, we are getting the time interval between when our first P waves get there, a little bit later, the S waves get there. There's a little time lag, okay? And each station will get that little, what we call the PS interval, that little difference in that time lag of arrival in there, okay? So between the arrival of the first P wave and the S wave at their location, 3 different stations. So a travel time graph gets used to determine each station's distance to the epicenter. So that little interval, that little time interval, actually gets translated then into a distance. So what that will tell us then, just from that little PS interval, is how far away from our seismographic station is the epicenter of the earthquake. It might tell us, oh, it's 1,000 miles away, or kilometers, whichever distance unit they use, away from our station. It doesn't tell us in what direction, okay, but some sort of a radius around our station. It's that many miles or kilometers, that distance away. Well, each of the other 3, all 3 stations will get a distance, okay, around them. So here's, the P waves arriving first. So here's the drum going by. P waves are the first to arrive. They're the fastest. A little bit later, S wave arrives, and then those surface waves, those L waves, right? They're the slowest of all, but of course they have very large amplitude here, so they do cause the most damage there. But we're interested in looking at when did we first get, the P wave, when did we first get the S wave, and what's that time difference? So we use the seismogram, that piece of paper, to determine that. Once we get that little interval, and they're on this particular example are saying that it's a 5-minute time interval, okay, from the time that the P wave arrived to when the first S wave arrived. It was 5 minutes, okay. So they go over here to that little 5 minutes. So this has time on the margin there, distance, and they're using kilometers across the bottom here. But that difference was 5 minutes, and so they come across to a 5-minute interval, okay? And they go down, and they're able to then get, it's looking like about 3,500 kilometers is their distance. That's how far away the epicenter of the earthquake is from the seismographic station that took the recording. Okay, so that's for one seismographic station. Of course, that gets repeated for the other 2 stations. And so whatever those distances are, and they sort of draw a radius around each of their seismographic stations, all 3 of them, using that method. And usually it will trilocate where all 3 circles overlap. That's your epicenter of your earthquake. So a circle with a radius equal to whatever those distances were. That first example was 3,500. The other 2 stations are whatever they're going to be, okay, around each station. And the point where all 3 circles intersect, okay, is where the earthquake's epicenter is. So trilocating all 3 places. You need at least 3 seismographic stations in order to get that. So those differences in velocity between the P and the S waves provides an excellent method for us. Of course, we use the travel time curve, or the time travel curve, to get that. So here's an example that they're using. So I said 3,500, but it was actually 3,400 at this Nagpur, okay, and then in India. And then they had a station over here in Darwin, Australia, okay, that was 4,900 kilometers is what their data gave them, okay. And then off over here in Paris, France, that distance was 8,200 kilometers. And so that from their data that they received at their seismographic station. So you can see the circles, the radius of that distance, okay? And they draw that for each one. Then all three overlap. So here's the Darwin, here's the Nagpur, and here's the Paris line, that orangey red one. And they all three overlapped at a single location, and that tells us that is the epicenter of the earthquake. So that's a nice little method you can use with the P and the S, those body waves. The seismic data for that really helps us do this. And for those of you in lab, you will get to try your hand at getting the epicenter of an earthquake using this method. So. Okay, so where are we finding all of the earthquakes on the planet? And again, plate tectonics really helps us with this, because a lot of these, the vast majority of these, are at those plate boundaries, okay? So 95% of the energy released by earthquakes are in just a few narrow zones that wind around the globe. This one's a major one, the Circum-Pacific Belt. I don't have my map down today, but around the Pacific Ocean, okay? Just think of the west coast of the United States, for example, out there by California, where the Pacific plate and the North American plate are converging, right? So a plate boundary right there, giving us, yeah, our volcanism, but also our earthquakes on the west coast. If you continue around the Pacific Ocean, I mentioned those volcanic island arcs coming off of the Alaska, Aleutian Islands I mentioned last time. All of those. So again, a convergence, but that time it was oceanic crust converging, but again, a plate boundary. But encircling, so the circumference sort of thing, Pacific Ocean is just a really, they tend to call that the ring of fire, because lots of volcanism, but also the earthquake seismic activity is going on in there. So Circum-Pacific Belt is a big one. The oceanic ridge system. So remember last time we talked about the mid-Atlantic ridge that just kind of goes right on through and winds its way around the Atlantic Ocean at the center. And that is that spreading center, so a divergent plate boundary right there along the mid-Atlantic Ocean ridge. That's another place, because we got motion. We got the pulling apart of crust, and so you're going to get a lot of seismic activity in there as well. Lots of volcanism too, but we're talking about the earthquakes right now. So yes, some places that we do see it, and this is a nice picture showing that. Should have something like this in your book, but okay, so North America, South America, and this is the Pacific Ocean, and again, all those little red dots in there. Here's our San Andreas Fault right there, all around, okay, all those Aleutian Islands come around, Japan, right, there's Japan, the Philippines, all of these places we mentioned, all in along through here. Circum-Pacific, they call that. Here's the mid-Atlantic ridge that they mentioned. So right along the Atlantic Ocean here, North America, South America, Africa over here. But right in through there, all along the mid-Atlantic ridge, the divergent plate boundary, we're getting seismic activity. So here along the Alpine Himalayan belt, okay, where India has slammed into Eurasia. So convergent, but continental convergence. So buckling up, creating mountain building, right? Creating the Himalayan mountains, the Alpine mountains. Now, remember how I mentioned that we don't get the volcanism with that type, continental convergent, but you do get the earthquakes with this. So yeah, that's another major belt for earthquakes along through there. But plate tectonics is clearly explaining these narrow zones that we see the majority of our earthquake activity. Okay, looking at some intensity, kind of how are we measuring our earthquakes? Intensity, so a measure of the degree of earth shaking, and based on the damage. So you're going to get damage that you can go out. They have surveyors that go out, just like in weather, when you get a tornado or something, they send out a crew to assess the damage based on the amount of damage. But that one has a lot to do with your building construction materials, your foundation. What are you using as your foundation? Because all of these are going to make a difference on how much damage you're going to get. Going back to George Christ's diary excerpt that we listened to, his log cabin was made out of wood, and it fared better than some of the other building constructions. Perhaps they were built out of stone or something like that. Those got completely damaged, but his little cabin did all right, he said. So it wasn't as bad. It's the flexing of the material. Also, your foundation. So what are you building on? So if you're building on loose, kind of unconsolidated material, it's not going to fare as well as if you built on a strong, solid foundation. So probably the worst building material is going to be brick and mortar, so brick masonry on a clay type of a foundation soil. That's going to be your worst kind of combination. But I do have a little, let me find it, something that demonstrates this is the Loma Prieta earthquake in California in 1989. Let's go to that one real quick. So here's where the epicenter is. There's San Andreas Fault running through. It's really a very long fault. There's San Francisco up there, San Francisco Bay in there. So the epicenter was actually right here, some 100 miles away from the Bay of San Francisco. And you can see from the color coding up here, this Bay area right here, okay, some 100 miles to the south was the epicenter, but that area there, very strong, severe damage, occurred 100 miles away, really strong. The reason is because back in 1906, when they had the San Francisco earthquake in 1906, all that damage and rubble that came from that, they kind of scooted that out and then built on it. I don't know, they must have forgot or something, but they built, okay, on that unconsolidated material from the prior earthquake, and it was not a very stable surface. So even though the earthquake was about 100 miles away, they suffered in the Bay Area a lot more damage than they should have because of the unconsolidated material that they built on. The Oakland Bridge collapsed during this one. Fires were all over the place because when you have an earthquake, the water lines will break, and then you don't have water to put the fires out. And things falling on people. So our little George Christ in his diary, that their little girl, Amanda Jane, died because a log fell on her. So things falling on people and fires are probably the greatest hazards during an earthquake. So this Loma Prieta, maybe better, well, maybe you can see that there, Loma Prieta earthquake of 1989. The damage in the San Francisco Bay Area was a lot more than it should have been because of the foundational material that the buildings were built on. All that rubble from a 1906 earthquake, San Francisco earthquake, years before. So foundation has a lot to do with what kind of damage you're going to get. So it really intensified the vibration because of that foundational problem. So that was the Loma Prieta earthquake of 1989 in there. So intensity, they are trying to go out and base the degree of shaking from the damage, but again, damage can be worse depending on your foundational material that you're building on and the material that you use to build your buildings as well. So do you have a steel frame? Is it all concrete sort of thing? So that becomes important. Magnitude then, so the magnitude scale, we think of the Richter magnitude scale. That estimates the amount of energy that gets released at the source of the earthquake. So this is more using the amplitude, the little squiggly lines, the amplitude from the body waves and surface waves as well that they look at. They get recorded on that drum of paper, that sheet of paper. So yes, the Richter scale is what that one's called. But the first one, the intensity scale that they're talking about, so how much damage is kind of seen and surveyed, an intensity scale. One called the Modified Mercalli intensity scale. It was developed using California building kind of standards. They are the ones that really have the most earthquake activity going on there. What their standard was, okay, for building damage, okay. So there's sort of kind of in there. But the drawback of intensity scales, okay, is that the destruction may not be a true measurement of the earthquake severity. Because if you got flimsy or poor construction of your buildings, you're going to get a lot more damage. If your foundation is unconsolidated material, like the Loma Prieta earthquake, you're going to get a lot more damage there. So it really doesn't have a lot to tell you for sure. It's not the best one of what the actual earthquake severity was. The Richter scale, so that one is better because it looks at the intensity. But this is the intensity scale as far as the modified Mercalli. So not felt would be like a 1, and then down here, masonry seriously damaged or destroyed, so brick material. Rails bent, so your train rails, railroad rails, bridges and things. Pipelines severely damaged, so we're talking really strong here. And then a 12 on that scale, nearly total damage there. So again, it's an okay scale for intensity, but it's got some flaws in it because what are we dealing with as far as foundation? What are we dealing with as far as our construction material too? Okay, Richter magnitude scaled, Charles Richter, so it's named for him in 1935. So of course we didn't have that scale back in 1811 and 1812 when George Christ experienced the New Madrid earthquake. So we didn't have that, but by best accounts and research of scientists, about a 7.3 to 7.5 on this Richter scale would have been the magnitude of the New Madrid earthquake. Okay. So it's based on that little amplitude of the largest seismic wave recorded. So the little blips, the little squiggles that we were showing you on that seismogram. Okay, so the amplitude. Okay, so many millimeters amplitude. Okay, and it accounts for the decrease in wave amplitude with increased distance. So the distance factor gets factored in. How far away from the earthquake was our seismographic station that was doing the recording? Okay, and so it does have sort of a distance on this scale. Okay, down the middle is the magnitude. Okay, and so this is sort of an exponential type of a graph here or chart, in that 1 unit of magnitude is equivalent to 10-fold increase in the amplitude. So the amplitude of the little, seismic waves, okay? Amplitudes over here in millimeters. But a 1 unit, so say we went from a magnitude of 1 to a magnitude of 2 on our scale, that would involve a 10-fold increase in the amplitude of our seismic wave, okay, in there. The amount of energy released is more like a 32-fold increase of energy for 1 unit of magnitude on our scale. So for example, let's just look at that. So say we were jumping up maybe 2 units of magnitude. Say we went from a 4.5 to a 6.5 magnitude. Okay, on our little Richter scale, so from 4.5 to 6.5. So we jumped 2 full units in there. But if each unit, so 1 unit increase, okay, is 10-fold in amplitude, okay, but for energy, the amount of energy, so 1 unit increase gives us I'm going to just round it like a 30, makes it easier to calculate, 30-fold increase in energy. Okay, so if we went from 4.5 to a 6.5 on the Richter scale, the amount of energy would have been 30 times 30. Okay, 30 times 30 equals 900 times more energy being released. Okay. And our amplitude is a 10-fold, so 10 times 10 would be 100 increase in our amplitude. Okay, so there's a little bit of different things going on there. It does tell us something about the amount of energy released and that amplitude of the largest seismic wave that comes across the drum there. But the amount of energy released is a 30 time per 1 unit increase, okay? And there's a 30 times 30 would be 900 times more energy a 6.5 magnitude would have than a 4.5. And as far as amplitude goes, a 6.5 magnitude earthquake would have 100 times greater amplitude than a 4.5. Magnitude on the Richter scale. So that's sort of a little bit of information that the Richter scale can give for us. Okay. And so magnitude less than 2 are not normally felt, at least by humans anyway. And then this is repeating kind of what I was saying there. Each unit of Richter magnitude increases to correspond to a 10-fold increase in the amplitude. So each unit of magnitude increase, 10-fold increase in the amplitude. And it's actually 32-fold increase in energy, right? But I rounded it to 30, so we could easily do a little calculation. So you might have a little calculation on the exam, so you want to make sure you can do it either for amplitude or for the energy released. Using something we would, 1, 2, 3 maybe units of magnitude we would go. And so make sure you could do a little calculation like that. So here was another one. It's kind of a Richter-like magnitude scale called moment magnitude. And so this one is estimating, none of those Richter-like magnitude scales really estimated extremely large earthquakes. And so this was used to get the actual displacement along the fault line. So how far did it actually, the Earth's crust get slippage? Okay, so displacement occurring along the fault line. None of those really adequately estimated the very, very large earthquakes. And so this moment magnitude is looking more at the displacement, how much displacement there was. So really the destruction that we talk about, and if you remember, I mentioned that things falling on people and fires are your greatest hazards in an earthquake. So in an earthquake, you're always seeing people trying to get outside of the building, so out in the open where things aren't going to be falling on them. I don't know if any of you have seen the movie San Andreas a few years back, but what they were doing was they were trying to go to that football stadium because out in the open in the middle, you were less likely to get things falling on you. So trying to get out in the open, but that's probably the greatest kind of hazards we have. But the amount of structural damage does depend on the vibrations, but how intense is it? Intensity and duration. So how strong is it? Yes, intensity, but for how long does it go on? Is it just a few seconds? Does it go on for several minutes? So how long is that shaking, the duration? That's a factor that could contribute to the structural damage. But I also mentioned the nature of the material upon which the structure is resting. So your foundation. So you don't want to build on shaky ground. So sandy soils, the clay soils that I mentioned, loose, unconsolidated material like they did in the Loma Prieta earthquake. So the foundation is important, and of course the design of your structure, so your building materials, the design of it, and so an A-frame wood's got more flexing that it can do than say the brick and the mortar, so the masonry type would not be good. So your design and your structure of your building as well there. So all of these play a part into how much damage you're going to get from your earthquake. So the worst kind of construction materials or combination of the site and the construction material would be your foundation that was clay, okay, and the masonry or the brick and mortar. Probably your worst combination is going to be those two. Brick walls on a clay site, okay, pretty bad. Ground shaking, so regions, okay, 20 to 50 kilometers from the epicenter is going to experience probably your worst. You're going to get the brunt of the intensity of the shaking. But, well, just like our Loma Prieta example, the 1989 Loma Prieta, California example, destruction varies due to the nature of the ground that the structures were built on. They should have known better out there in California not to build on all that rubble from the 1906 earthquake that they filled in there. So that Bay Area got more severe damage than it should have because of that loose, unconsolidated material that they built on. And that loose, unconsolidated material almost acts like a liquid. They call that liquefaction. And it will flow, almost like quicksand kind of thing. So not a good combination there. This is a great example of the Anchorage, Alaska quake, the 1964, where I showed you the seismogram of that, the little amplitudes of the seismogram that was from this earthquake. But the interesting thing is this little building right here, okay, I don't know, I can't remember if that was a JCPenney's or one or the other was a JCPenney's, but this one you can see is concrete structure. This one is more of steel, it's glass and steel form in it, so the structure, the building materials were different. Your concrete one, so the brick and mortar walls, most damage right there. It doesn't flex, so that material doesn't flex well as, say, your steel or your wood frame materials. And so, yeah, that has a lot to do with the amount of damage you would get is your building materials as well as your foundation. So there are things we can do to try to limit the destruction within reason, right? With our building materials and our foundation materials. So liquefaction, as I mentioned, the unconsolidated materials, well, there's a lot of pore space, lots of cracks in there that water can get down into, and it will just flow like a river. It will turn it into a mobile fluid once that gets saturated with water. And remember, in earthquakes, a lot of those water lines do get broken, the pipes burst, and water's going everywhere. So it's getting down into that unconsolidated material. We call that liquefaction. And so that just turns it into a fluid-like material. Tsunamis. So tsunamis are earthquakes that are occurring on the ocean floor. So within the ocean, you remember we've got the Mid-Atlantic Ridge, right? It wants to move apart. Other places are coming together, convergent, creating all those volcanic island arcs out there. So we do have plate boundaries out in the ocean. And so we call it a tsunami when you get the vibrations, so the seismic waves, sea waves, and we got water involved. And it will create very destructive waves, very large surges of these waves, inappropriately or incorrectly called tidal waves. They have nothing to do with the ocean tides, which are astronomical forces of the sun and the moon. I think we mentioned tides last time when we were talking about continental drift and Alfred Wegener's mechanism, right? Not appropriately called a tidal wave at all. Nothing to do with a tide. It has to do with the seismic waves that are occurring from the slippage of the earth within the ocean, at the ocean floor there. So yeah, tsunamis. I'm wondering if I have my picture. I might have a picture of it, but that vertical displacement along a fault on the ocean floor, triggering like a landslide, something like this, creating the release of energy. So in the open ocean, the height's not very high. So when you're in deep enough water, your wave isn't that great, less than a meter. But once you get closer to the shoreline, the bottom of your ocean, the seafloor gets shallower and shallower, and you're building up in the wave height as you get closer and closer to over 30 meters high. And so these will come up. What you initially start to see is a receding of the water away from the shoreline. If you ever witnessed that, where all of a sudden the water is receding from the beach area, from the shoreline, okay, that means there is a tsunami wave coming. It really recedes out towards the ocean, and then this wall of water comes. Let me see if, don't think I have it in the PowerPoint, so let me switch over real quick of a 2004 tsunami in Indonesia. Okay. Here we have people out in the ocean, and you see a lot of the shoreline here where the water is receding. Okay, going back towards the ocean. And then you see this wall, this big wave on its way. And unfortunately, these people are running, but too late because they did not survive that wave. Okay, so unfortunately, that's kind of a sad picture there. But 250,000 people died in this 2004 tsunami in Indonesia. Okay, and so afterwards, they sort of had a lot of damage. Here's kind of the after effect of just a hodgepodge of debris that water can pick up and move around. 250,000 people lost their lives in that one. Fortunately, though, tsunamis can be warned because we get the seismic information that there was an earthquake that happened out in the ocean, on the ocean floor. And a lot of times it takes several minutes for that wave, that energy through the water wave to reach the land. And so sometimes they can get maybe 15 minutes of warning time to evacuate and get to higher ground. But caught unawares, if you're out and you can't hear the warnings, yeah, you could get caught out in that, and you just can't outrun those waves. So, oh, and here's one from Japan, that a bit of wall of water there. Just picking up those cars like they were nothing, but a big breaching the water, the highway there. But this was a 2011 tsunami in Japan. So yes, these are earthquakes that occur out on the ocean floor, and then the wave that comes, the seismic wave, water is getting pushed along in those locations. Tsunami. Okay, and that was just a depiction of, okay, here we have our plate boundary, and we have a subducting plate, okay, a convergent plate boundary, right? And here's our continental plate, there's oceanic, and you're getting, okay, the earthquake, the epicenter, the focus there, of course, that's going to radiate out energy in all directions. But it's not quite a problem when you're out in deep water. Your wave's not going to be very big, but it's when you start getting into shallower water, as your seafloor topography changes, your wave is going to build higher and higher and higher as you reach your shoreline. And so that big wall of water comes up and just decimates everything in its path. Okay, so earthquake destruction, again, landslides and ground subsidence, things falling on you, definitely a big hazard, and fires, like I mentioned, the water mains lines burst, and they have nothing to put the fires out, so that is definitely some destruction that goes on. So something that we can use, these seismic waves that we had up there, the P and the S waves, and that can probe the interior of the Earth. So everything we know, well, not everything, but a lot of what we know about Earth's interior comes from seismic activity, the study of those P and those S waves, and so those body waves. So if you remember, I mentioned that the P waves can travel through solid, liquids, and gases, but the S waves can only travel through solids. And so one of the ways we learned about our core, that we have sort of a liquid outer core and then a solid inner core, is from our study of these seismic waves. The P waves would make it all the way through to the other side, okay? It would be going through solid, liquids, and gases, but the S waves only go through solid. So the S wave would come along and it would get refracted, okay? Reflected, refracted. It would not go through the liquid portion, okay, and then it'd come out kind of on the other side. And so from that information, we were able to learn that we have a liquid outer core and then a solid inner core. And so probing of the interior of the Earth, we do use seismic activity to help us. So we know kind of that the outer core is thought to be liquid because the S waves stop at that point. P waves can go ahead and go on through solid, liquids, and gases. So yeah, and depending on what kind of material they're going through, you know, they'll bend in a certain way. And so we can study the interior of the Earth using that. Something I don't think that's in your PowerPoint is that we can actually use meteorites. So material coming from space, sort of leftover kind of material, coming from the building blocks of what built up our planets. This meteorite that I have here. But there's evidence of nickel and iron composition in Earth's inner core. That's coming from these meteorites. This one is sort of an iron, stony iron meteorite. It has iron and nickel and the silicate type material as well. And so the building blocks that built up our planets are similar for our terrestrial planets. And so anytime we can get material either from asteroids or comets, little pieces of comets, it can tell us something about our interior. And so they're basing these from the densities of material through the planet. And it is coming and stemming from this idea of the meteorites that we have an iron and nickel core, a very dense material. And so that's just a little piece of a meteorite that I have there from Brenham, Kansas. So just a little bit on the evidence there of the nickel and iron within the core stemming from what we learn from meteorites. So little things that come from space and actually make it to the Earth's surface. So yeah, and so I think we've seen this picture before, but that very thin crust layer, right, includes the oceanic crust and the continental crust, okay, with a small portion of the upper mantle together. That's called the lithosphere. I know you probably can't see the little writing on there, but you have these pictures on Blackboard for you. And then the asthenosphere, so that fluid, flowy, kind of hot plastic, mobile, so it's solid, but yet it flows. I kind of liken that to a warmed candle wax. Not to the point that you're melting it, but to the point that you can form it and bend it. So it just kind of flows, mobile. The asthenosphere, so you have the lithosphere riding over that kind of mobile, moving asthenosphere, plate tectonics going on. The very high density rock of the mantle, and then our core, we've got the iron and the nickel core, and then that outer sort of liquid core as well from the seismic information. So kind of probing the interior of the Earth, we're able to figure out and put together what the interior of the Earth might look like. So that's a lot of the earthquake portion, explaining the seismic waves, how we can find the epicenter, the structural damage, building materials, foundational structures as well. So the next part of this is looking at the deformation, structural deformation. And we can get some features that we do have some names for in there when the stress is applied to it. Earth's crust. So deformation refers to all changes in the original form and size of the rock body. And again, sometimes the stress, if it's long term, is it short term, that does have an effect on this. But most crustal deformation is going to be occurring along those plate margins, so those boundaries where we are having an interaction between the plates, so converging, diverging, or shearing past one another. Okay, so along plate margins, or where we see the majority of the deformation. So deformation involves some sort of a stress, and so this could be a compressional stress, so pushing together, right, compressing, pulling apart, which we call that tensile or tension, okay, tensile, sometimes that's called, or that shearing motion. So these are some stresses that are applied to a given area, okay? And we can set up these different types of formations that we talk about here. An elastic formation. So this would be something like our earthquake, where we put the stress on it. So elastic is a good one here. Okay, we put a stress on this, and once that stress is released, the material goes back to its original shape. Okay, same thing with a rock. The rock will return to its nearly original size and shape once that stress is removed. And we call that elastic, okay, because it will go back. However, if we exceed our elastic limit, so the strength of the rock, it's going to do a couple of things. One is we call ductile deformation, where it will flow, kind of plastically flow, or it will be brittle deformation, brittle in the fact that it breaks, okay? It will rupture, okay? It will fracture and rupture. So either ductile or brittle once you exceed that elastic limit, okay? So a couple of things can happen when we have our various stresses. And so example of a ductile, okay, deformation. Okay. So during crustal deformation, rocks are bent into a series of wave-like undulations that we call folds, okay? So these folds are either going to, fold upward, piece of paper here. We might fold upward, or we might fold downward. So what we call folds, and that's like the terminology of it, the structural deformation is a fold, the product of the deformation. Okay. Compressional stress. So if you notice when I was doing that with the piece of paper here, I was pushing together each time. So I'm pushing together with my hands, and I have an upward arching bend or a fold. And again, I'm pushing together, so compression, and I have a downward fold in there, a downward arch. And so these are known as anticlines and synclines. So the anticline is the upfolded arch, okay, the upward arch. That's an anticline, okay, an arched rock layer. The syncline is the downward, okay, fold or trough on the rock layers, okay. So that ductile, most common type of folds here, anticlines or synclines, okay, are the most common fold types. Okay. These here we won't be too interested in. We're just going to keep it simple with the anticline and syncline, but you can get them where they're not real symmetrical, they're a little off, skewed, a little bit asymmetrical, or they might be really overturned. But for here, we'll just be interested in the anticline and the syncline for the names of our folds. And here it is, have an example. Now, I am not sure how this was taken out of the ground, but you see here several rock layers, okay? A little layer there, a little layer there, a little layer there. And this one is the upward arched, and when I'm holding it in this direction, would be an anticline. Well, if I turn that over, okay, everything's arching downward, and that would be a syncline. So, I don't know how this was taken out of the ground with my sample here, because I didn't collect this, but this is either an anticline, this way, or a syncline. So you have several layers of strata in the Earth's crust, and because of that stress that was put on it, that compressional stress, and this flowed, okay, and created the fold of the anticline and syncline. very common. So that was from the Nevada Ruby Mountains, that particular sample was. So here in, okay, that's a nice picture. So anticline, the upward arch, syncline, downward arch. Here is if you get it a little off center, so asymmetrical fold, and here is if it just really overturns, an overturned fold. But anticline, syncline will be fine. Here in Arkansas, the Ouachita Mountains, we do have examples of anticlines and synclines. And I've mentioned before how the Ouachita Mountain region really did suffer a lot of structural deformation with the assemblage of Pangea. If you remember that from last chapter, the coming together of North America, South America, and even Africa. So the assembling of the supercontinent Pangea. Really, the Ouachita Mountain region suffered a lot of deformation. So we see a lot of anticline and synclines with that, and to the point that we have these thrust faults, so kind of these reverse faults that we'll talk about the faults next. But pretty intense damage with the folding of the rock material. And so that's a good example of the in the Ouachita Mountain regions, the anticlines and the synclines there. And we do have some thrust faults as well. We'll talk about that with our faults coming up here in a second. But the Ouachita Mountain region, pretty severely deformed there. Oh, before I go from the camera here, there is a place in the Arkansas River Valley that you could see a really good anticline is in Morrilton. Like you can drive through it on the highway. So on each side of you, you've got sort of this panoramic view here of an anticline. So we cut a road right on through an anticline. And so on either side of you, you've got an anticline in the Morrilton, Arkansas region. So if you wanted to drive through and visit that, there is an anticline in Morrilton. Okay. So some folds that, if your compression, okay, is coming in at all directions, so sort of circular compression. If you get an upward fold in a circular compression, it forms what we call a dome. Okay, so a dome. I don't think I have anything that looks like a dome for us here, but it's upward displacement, circular, oldest rocks in the center, youngest rocks on the outer flank. So all that material just sort of folded up and created this sort of dome shape in here. All of your rock layers kind of, but circular, okay? Almost like an upside down bowl shape, a dome, okay? And then the opposite of that is a basin, so a downward kind of folded region here. Kind of like a bowl shape, so they call that a basin, okay? For your domes, you've got here closer to home in Arkansas, the Ozark Mountains is a dome. So back to our little handy dandy picture here. But in the Ozark Mountains, this is just a portion of the dome. It actually continues up there in Missouri, the dome does, but sort of this folding but circular, and this is sort of the outer flanks of it here in the Ozark Mountain region here in Arkansas. Another kind of famous dome is the Mount Rushmore in South Dakota. Yeah, that's a good one to go visit, but Mount Rushmore is a dome, also a good feature there, a domal feature. Okay. So those are examples of folds. So you have your deformation where the rock is kind of flowing, okay, ductile, they call that. The brittle deformation is you're going to get a break. It's going to rupture. And so those fractures, when it does rupture, we call those faults, okay? So the faults are where the movement is primarily vertical, okay? It could be vertical, horizontal, or oblique, but we're going to classify them depending on, well, what is that relative movement that we're seeing? So where you're getting that mainly vertical, let's see, I may try to do a drawing for this. And I brought my fault blocks as well to maybe help us with this. Okay, let's see here. Okay, I've got a little minor here because there's some mining terms that they use to talk about the terminology in here, like a hanging wall and a foot wall. And so these are some minor terms that in the history of it, where the name comes from. So here's our little miner, and he's digging out, and the reason they want to dig, here's our fault line, okay, cutting across the rock, the break in the rock, so the fracture, the fault in there. And they'll go in because along those little fractures, a lot of that rich material fluid gets down in the cracks and then crystallizes out. And so you can get some gold, you can get those quartz crystals, things that are little pockets of good things that the miners are after. And so they're wanting to dig their mine right along the fault line, is what they're trying to do. And so some old mining terms is on this side, okay, of where the miner's head is, we call the hanging wall. So over here is the hanging wall, like where he would hang his lantern, something like that. Down here where his feet are, so this block down here is called the foot wall. Okay, so that's where that terminology is kind of coming from, the hanging wall and the foot wall. And so depending on the movement, okay, so we got to get movement along that fault line. Does the hanging wall move up or does the hanging wall move down in relationship to the foot wall is what they talk about here. So if you get that sort of vertical kind of motion, okay, that's a dip slip, they call that, a dip slip. So a dip slip where you get the hanging wall moving down, okay, is called a normal dip slip. It's going with gravity, so they kind of call that one a normal dip slip. Get my fault blocks here. Okay, so here we have some crust, and you can see actually two here. But if I am moving, okay, the crust and that hanging wall, so you got to envision our little miner across this fault block here, okay, across that fault line, and the hanging wall. So his head, I'm trying to hold on this. This would be the hanging wall, that piece right there. Okay. So when I pull these apart, okay, the hanging wall moves down. Okay, relationship. So think of where his head would be. The hanging wall moves down. That's called a normal dip slip fault. Okay, so where the motion is vertical like that, we call that a dip slip fault. Okay. And notice that I'm pulling my hands apart, pulling apart. So that's called a tensional or tensile type of a stress, pulling apart. And you get a normal dip slip fault. Okay, now imagine where the hanging wall is, so that center block there. And I push together, so I compress. Okay, I push together. Well, that hanging wall goes up. And so that is called a reverse dip slip fault, a reverse. Okay, so hanging wall moves up. And the stress is compression. Okay, I'm pushing together. So we can get either a normal dip slip fault or a reverse dip slip fault out of this. Okay, so dip slip fault includes a hanging wall and a foot wall, and depending on does that go up or does that go down. Okay, the normal is when the hanging wall block moves down. Okay, so that hanging wall block would go down. Okay, like I showed you with mine there. So it's accommodating lengthening or extension, so the pulling apart, tensional type of a force in there, okay, stress, okay. Extension of the crust. And some larger scale normal fault structures are called fault block mountains. And so you can actually get some terminology here. I'm not sure if they share that with us, but I'll try to draw something here for you. Got some layers of rock here that we can look at. So that'd all be the same rock layer at one time. It's kind of been pulled apart here though. And so when it did get pulled apart, okay, the hanging wall dropped down, right? So they do call those the fault block mountains. But the part that's up, they call that a horst, H-O-R-S-T, and the low one down is called a graben, G-R-A-B-E-N, a graben. And again, this would be a horst over here. Okay, a horst and a graben, horst and a graben. And so you can get these fault block mountains, and they just kind of repeat. Okay, and it's all due to this tensional, right, extension of the crust, so the pulling apart of the crust, and you get that drop down, that little fault block. So when I pull apart again, drops down. So the one in the center becomes the graben, and then these two outer ones, the horst, or some terminology. So a very deep graben, and we see this out towards the west, the desert kind of southwest region. Out there in California, Death Valley, right? Death Valley is a graben. It's one of the very low down ones. So Death Valley in California is in a graben, an excellent, kind of iconic example of a deep graben. Okay, so we get a lot of that kind of out towards the southwest part of the country. So then next, this is a nice picture of it, of a normal fault. So you do see, it's much better than my drawing, but you do see the extensional or tension or tensile, all kind of mean the same thing, the pulling apart. And the hanging wall moving down. That's called a normal dip slip fault. Okay. The reverse and thrust faults. So I mentioned the Ouachita Mountain region has thrust faults, okay, in these reverse. So this one, the hanging wall moves up in relative to our footwall block. So these can be, you know, greater than 45. Thrust faults have less than 45. So depending on the angle that we're seeing that motion, but from strong compressional forces. So the reverse kind of dip slip. I'm compressing, I'm pushing together, and my hanging wall moves up. Okay, that's a reverse dip slip fault or a thrust fault, they call those. And the Ouachita Mountain, that great compressional force that it went under, we do see some thrust faults in the Ouachita Mountain region here in Arkansas. another one. So strong compressional forces will give you that. There's your reverse, the coming together, hanging wall moving up this time, or reverse. So it's like it's going against gravity, so reverse kind of thing. Lots of compression to give you this. Now, some other types of faults we call the stress is more of that shearing motion, more like our transform fault boundaries, where we're not coming together convergent, we're not pulling apart divergent, but we're shearing past one another. So that stress of shear, okay? These are known as strike slip faults. So the displacement is more horizontal rather than vertical. Okay, these were vertical. The strike slips are more horizontal and parallel to the strike of the fault. And so it could be to the right or to the left. It just depends which way it's going to shift. So I've got, looking from the top here, a little fault line, a little break in there. But this time it's going to be more of a horizontal motion. And so my little stream that's going through the middle of this, if I either go to the right or I go to the left, but laterally, okay, so in a horizontal fashion is the motion here with a strike slip, okay, and so we would call it a right lateral strike slip or left lateral strike slip, depending on which way the motion was, and kind of the way we figure those out. Okay, hopefully you can see the board over here, but this would be a strike slip fault. Okay, so say I have my block here. Okay, and here's the fault line. And let's say that was our river kind of thing that went through there. But depending on, say that block went this way and that block went that way, you stand on one side of the fault line, so right there, okay, we stand on that side and we look across the fault line. And whatever the direction the motion is, you'll either call it right or left, lateral. So here we are, standing on this side, and we look across to the fault line across it, and we notice that everything went to the right. So that would be a right lateral strike slip, is how we would term that. Right lateral strike slip. And it didn't matter which side of the fault you were on. I mean, you could have been on this side and looking across this way, it still went to the right, okay, in this particular example. So they're saying as you face the fault, we're facing the fault, and the opposite side of the fault moved to the right. That's a right lateral strike slip because it's a horizontal motion. Strike slip. Or left lateral if as you face the fault, the opposite side of the fault moves to the left. So when we talked about the San Andreas fault, that's a transform fault. And it happens to be a right lateral transform fault. So we have that shearing motion. And the San Andreas fault ends up being a strike slip fault, and in particular a right lateral strike slip fault for your San Andreas fault in California. Okay, so yeah, remember how San Andreas separated the North American plate and the Pacific plate? If you remember that, Parkfield, California had that little bridge that crossed that. One place you're entering the Pacific plate, and the other one the North American plate of that bridge of the San Andreas fault. So that is a strike slip fault. It's a right lateral strike slip fault because that motion is of the Pacific plate and the North American plate shearing past one another on the San Andreas fault. Right lateral strike slip fault. And again, here's our nice picture of that. So this is going in a horizontal fashion, a shearing motion, and these are strike slip faults. So the vertical ones were the dip slip faults, okay? That this is a strike slip. And so if you were on this side of the fault line looking across across, that would be a right. Well, it didn't matter if I was on this side and I'm looking across. Again, motion is to the right. So that's how you figure out your strike slip direction in there. Okay. So strike slip faults, yeah. Transform faults. So large strike slip faults that cut through the lithosphere accommodate the motion between large crustal plates. So that's San Andreas strike slip faults. Transform boundaries, if you remember those from our several types of plate tectonic boundaries, was a transform type of a fault. So that's a horizontal motion, a shearing motion there. There it is, the San Andreas fault system, and it's very long. You can see that goes quite a ways there. Yeah, all up and along through there, and so that is a strike slip type of a fault. Transform boundary. Now I thought they didn't really include it, but your book includes a little bit about the mountain building. So we did talk about mountain building in the plate tectonics, where you can get continental volcanic arcs up on the continents when you have a convergent plate boundary. So think of our west coast, Mount St. Helens, Mount Rainier, all of those sort of volcanic, continental volcanic arcs, plate boundary. You get those volcanic island arcs, like off the Alaskan coast, the Aleutian Islands, Philippines, Japan, when you get oceanic convergence, okay? And you can get some mountain building when you have the divergent along the mid-ocean ridge, mountain building with that, and continental convergence. Remember, two continents coming together. So the Himalayan mountains, the Alpine mountains, where were built up when we had the collision between India and Eurasia, Asia in there, and it built that up. Those don't have volcanism with them, but they do have the earthquakes with them, but the buckling up of the crust. So yeah, the Himalayan mountains are forming when continental crusts converge and come together. So all those plate boundaries do explain the mountain chains that we have. So yeah, plate tectonics, that overarching theory that really does make geology make sense. And we saw a good example of it in our talk about the earthquakes and the structural deformation of the folds, so the anticlines and the synclines, the domes and the basins, and then our faults. So our normal dip slip faults, reverse dip slip faults, and then our strike slip type variety of faults, the right lateral and the left lateral. So some structural deformation that does come from the stresses of compressing, coming together, tension pulling apart, or the shearing motion. So those variety of stresses that we get at our plate boundaries is going to give us all manner of geological deformations and some of the terminology associated with it. But that does conclude chapter 6, and in chapter 7 we're going to look more closely at the volcanism aspect of plate tectonics. And so this was, more of the earthquake side of it, structural deformation side of it. But then next we do want to dive a little more into the volcanism, variety of volcanoes, and hazards and things that go with that composition of our volcanoes. So until next time, bye for now.